Hello, everybody. You tuned into today's PIR live event. I'm your host for today, Kevin Kugler. It's my pleasure to be with you. Our guest today is Francesco Tangorra from Algonquin College up in Ottawa. Francesco teaches civil engineering, structural engineering, and construction engineering. He specializes in failure analysis, collapse investigation, building code compliance review, and structural damage assessment. Welcome, Francesco, to the show, and thanks very much for taking the time to be with us.
You're welcome. Hi, everybody.
Before we get started, I'd also like to welcome all of you, the viewers, who are watching from your classrooms. Thank you for taking the time to be with us today, and we're glad that you are. If you are watching the live stream, remember you can tweet your questions to our hashtag AskPIR at any time throughout the event. If there's room in your tweet, include your name or your city so we can give you a shout out live. Look forward to getting to some of your questions in a moment because I know some of you have already sent some in, and that's really exciting. Thank you. But right now, let's welcome our guests appropriately. And Francesco, maybe you could tell us a little bit more about yourself and what you do.
Absolutely. Thank you very much. Hi, everybody. My name is Francesco, and I teach here at Algonquin College as a professor in civil engineering technology. My professional background is in collapse analysis. So I'm kind of a backwards structural engineer as opposed to being brought in to help design and get buildings to come up from the ground up. I actually have been called in to determine why a building has collapsed or a similar type of structure like barns, homes, and the like. So I worked for almost 8 years in that capacity in private consulting. I'd be called in the event of, say, heavy snowfalls and if there were issues with buildings. In the event that, say, a home exploded and to investigate the cause and the effects of that explosion on neighboring homes. In the event of the demolition of stadiums and so on and so forth. At the same time, too, I then started teaching here at the college, and I've been teaching here in that capacity for almost 6 years now. So I have a bit of an odd background when it comes to being a structural engineer. I have done a lot of design of making sure the structures stay up and are strong and stay there for a long time. But a lot of my background is, in fact, with figuring out why they have come down.
You know, I wanted to ask you a quick question, and thank you for that. A friend of mine is a civil engineer, and he was telling me not too long ago that we're at end of life with a lot of our bridges across Canada and the United States, and he was quite concerned that we're going to start to see more of these collapses as these projects come to end of life. Could you talk a little bit about that? Is that a serious concern? Is that really the case right now in North America, Francesco?
So the answer is yes and no. All structures, whether it's a bridge, a house, an office tower, a barn, they are designed to withstand only so many hundreds of years or decades of years worth of forces. So maybe that might be 10 years, 30 years, 50 years, 100 years. But when it comes to structures like, say, bridges or schools or hospitals and the like, they actually also have a maintenance program in effect, whereby they get inspected fairly regularly to make sure that we know well in advance when that end of lifespan approaches, so that maybe a decision can be made to repair and increase that lifespan or demolish and replace. That is especially true for bridges. And especially in North America, we have thousands of bridges. So there's a huge effort in place actually with inspecting them and keeping these inspections current and up to date to make sure that they're still okay. As it turns out, in fact, many of our bridges have gone well beyond their expected lifespan. And that's not because it wasn't expected to happen, but simply because maybe it was more economical to do some repairs and keep them as they were, as opposed to, say, demolish them, inconvenience everybody with traffic issues, and then build a new one.
What do you say we take some questions from some students, Francesco?
That'd be great.
So here's one from Roderick. Roderick is from Ms. Clark's class. I'm not sure where that is. But they're very active today, so we're getting quite a few tweets from them. Have you ever worked with bridges that have collapsed from earthquakes?
So I personally have not. And as it turns out, typically there aren't too many bridges that will collapse as a result of earthquakes. So, first of all, personally, I have not worked with any bridges that have collapsed as a result of earthquake. And no, not too many will collapse as a result of earthquake. Usually that's something that we really make sure that we build against to make sure that a bridge will resist the force of a seismic event, of an earthquake.
Okay. Thank you for that. Good question, Roderick. Here's one from Austin. Why is steel so much stronger than wood, even though they can both rust or rot?
Right. That's an excellent question. So one of the big differences between steel and wood is that steel is a man-made material, whereas wood is a material that's harvested, right? You go to a plant or a tree that's big enough and you cut it into pieces that will then turn into wood. The other thing about steel that's different from wood is that if you take a piece of steel and you squish it or pull it apart in any direction, right? If you have a cube and you do that in any direction, it will behave exactly the same way. Because wood is a natural material, it makes a difference whether you squish wood in one direction versus another. And that's because as a natural material, wood was not originally made to support homes. It was there to support a tall tree. So it's been evolved so that it will support all the forces that come from being a tall tree, which means that maybe, depending on how you've harvested that piece of wood, it will behave differently in different directions. As for the rotting and rusting aspect, you're absolutely right. Both wood and steel will suffer from environmental damages, but luckily we're pretty good, and by that I mean people are pretty good at maintaining structures made out of wood and steel, whether it's with new coats of paint or with a shellac on the wood or similar. That's an excellent question. Thank you.
Building on that, then, if trees are designed naturally to withstand forces, from the right or left, the swaying of the tree, so they're fairly strong, obviously, from that perspective, from the sides, would they be weaker then from forces coming from the top or from the bottom?
As a tree, typically, yes. So that's why you'll see that when it comes, a good example of a load that's doing this on a tree would be, say, snow. We're very familiar as Canadian with snow on trees. So what a tree will do is that instead of putting out flat surfaces for its branches, it puts out branches that look a lot like this, so the snow can actually fall through. Pine trees with needles are really good at doing that, at shedding the snow off of it. So yeah, definitely trees not made to take this kind of load in nature, really more made to take this kind of load in nature.
Good, thank you for that. Here's a little more advanced question, I think, for some of the older kids out there. This is from Drew. Drew says, how do you best design a suspension bridge to overcome aeroelastic flutter, similar to what happened to the Tacoma Narrows Bridge? Maybe
That's a fantastic question.
Can you maybe let us know what the Tacoma Narrows Bridge is first?
Sure. Believe it or not, building the long bridges that we're familiar with is a relatively new science. And an example of that is the Tacoma Narrow Bridge. Until then, the science of building these long, slender bridges had not been well evolved. And what happened with the Tacoma Narrow Bridge is that the bridge was very long and also very thin. And what ended up happening to that bridge, because it was crossing over a river, is sort of like a blade of grass when you blow it in the wind and you're holding it. It started to flutter with the wind. And it got to a point where this bridge fluttered so badly that it basically broke itself apart. From an engineering perspective, from a failure analysis perspective, this is really something really incredible to watch, because you're watching steel and concrete bend as if it were a flexible twig of wood. But that's basically the issue with it. And that's why, since then, the science of bridge design and especially for fluttering and wind-induced vibrations, has really exploded. So then to answer your question directly, the best way right now to actually design and analyze these bridges is to build a scale model, so a smaller model of this bridge, to put it in a wind tunnel and to test it. So to actually subject it to the expected weather conditions and winds for where you're going to put that bridge.
Another question from, I think this is Ms. Swallow, Jen Swallow's class. I'm not sure where the class is from. This is from Evan, and Evan would like to know if you've ever dealt with train bridges.
I personally have not, I admit, but train bridges are a bit of a passion of mine. That's a great question. So all I've really done personally with train bridges has been to admire them, especially the older ones that you get to see in Europe or the middle of the USA, those steel bridges. Some of them are really gorgeous and beautiful. But personally, no, I have not dealt with train bridges.
You know, I was on a trip out to Prince Edward Island a few years ago, just after the Confederation Bridge was built, and I went across the bridge, which was an interesting adventure in itself, driving that.
Yes.
Have you ever been across that bridge?
I wish. It's on my bucket list.
Yeah, it's fantastic. You know, it's a little nerve-wracking, but yeah, it's fantastic. And you get to the other side, and there's like a discovery center or something. They talk about some of the challenges that they had when building that bridge. And for you students that are out there and you're not sure what we're talking about, this is the bridge that connects Prince Edward Island to the rest of the Maritime, so coming off of New Brunswick. And it's, I can't remember the exact distance, but is it something like 10 or 15 kilometers?
It's huge, yeah.
Yeah, so it's pretty amazing. And it goes across the straits, of course, which are, torrential waters that come down there at different times during the year. So, and there's ice flows that come down, and the engineers, I guess, were, trying to decide how are we going to withstand the force of those ice flows that's coming down the strait. And I forget the name of the strait down there. You might know it. My geography is terrible. But, and they came up with a really unique design on the pillars that support the bridge. And I think that I recall what it is, but do you know what I'm talking about, Francesco?
Sure. I'm actually, I believe I have an image here that I'm going to bring up in a moment for everyone looking in. But if you want to get started, then I'll bring that up. Absolutely.
Perfect. Yeah. So as I recall, and correct me if my memory is failing on this, but they were concerned about these ice chunks smashing into the columns and eventually just exerting so much force upon the columns that the bridge would collapse. And so they thought, well, rather than build a bridge that can withstand those amount of forces with their columns, we'll not try and fight Mother Nature. We'll try and build a gently sloping column so that the ice moves up and starts climbing up the column toward the bridge and then eventually breaks apart. I think that's correct, but let's see if we get a picture of it here. There we go. Yeah, that's a great picture.
So you can actually see how the columns from the bottom, where it's hitting the ice, are larger and taper up. It's essentially mimicking sort of like an icebreaker geometry, if you will.
Yeah, we lost the image there, but and we did have it for quite a few seconds. Amazing, that bridge just seems to extend into the horizon, and you don't see any land on the other side. It's like you're driving into the ocean.
Yeah. So and you may not know this, viewers, if you're tuning in, but it turns out that this bridge actually has been designed the way that it has for a specific reason. So the bridge actually is not simply a straight bridge, a straight line. It actually goes up at an incline and then actually curves near the end of it. The issue with it is that you might get tunnel vision as you're driving through this straight bridge with nothing around you, and you end up actually getting hypnotized by it. So to avoid, say, driving off this bridge, they've introduced these this geometry to the bridge to keep drivers alert and paying attention. So that's why the bridge goes up at an incline at the start and at the end of it, and it also curves near the end of it.
I didn't realize that, but I found myself getting tunnel vision in different scenarios while driving, so I can certainly understand that.
Right.
How about another question?
Sure.
This one's again from, I don't know if this is the same Roderick or not, but he'd like to know if you investigated the earthquake in Nepal at all.
So no, I have not personally investigated it, but I have been following it. It's a terrible tragedy, and something that's really resonated across the world. There's been a huge support from everywhere in the world for this terrible event. It turns out to be somewhat of a seismic zone, but if you noticed, my guess would be that not a lot of their buildings were designed to resist an earthquake of this magnitude. And to be clear, this was a huge earthquake. I mean, even by our standards, this was a huge earthquake that occurred.
Here's another question. And this one's a little more of a higher grade, I think, that maybe this is coming from. But are there different degrees or levels of safety factors that are used when designing different types of buildings? And if there are, why wouldn't you just design everything the same?
So I guess there are two questions in there. Question number one is and that's a great question, if there are various degrees of safety factors that are embedded in buildings and structures. And the answer is yes, absolutely. To give you a simple example, if you've ever been in a parking garage, right, the ones that are made out of concrete and you find them outside of a mall, if you were to take out one of the columns in that parking garage, it would still stand up. And that's where the different degrees of safety come in place. So the reason why all the buildings are not made the same is because, well, and this is true, they would all be very boring if all the buildings were the same. That's why architects are so great. They give us an opportunity to turn buildings, bridges, into statements, into pieces of art. The other one, too, is that sometimes, depending on the building, it's simply not feasible. We cannot afford to introduce a huge degree of redundancy, a huge degree of safety. So that is why other methods of building have been researched and developed to come up with that. A good rule of thumb is the more the building is important, usually the higher the degree of safety in it.
Those are some great questions, everybody. Thanks for keeping those coming, and that's quite a few that we've had already. But we have time for more. If you'd like to tweet them out, it's AskPIR is the hashtag. In the meantime, though, Francesco, maybe now is a good time to talk a little bit about the Popsicle Stick Bridge Challenge.
Yes. So this is a challenge that I've been trying to run with my students here at Algonquin College, and there's been some mixed success. I mean, our students are really busy and they don't always have enough time to dedicate to something like this. I've brought with me an example of this year's winning bridge. I'm just going to back up a little bit so I can show you what this bridge looks like. So you'll notice that it's generally almost like a triangle. And for you students out there, some of you have likely learned by now that triangle really is one of the strong, if not the strongest shape in building structure because it's the simplest. It has three sides. And so this was the bridge that won, and you can actually see where it failed, right? So a load was put on this bridge here, and after it reached its maximum load, that's where it failed. And if you can actually see it, if I tilt it properly, you'll notice that that's actually a beam made out of multiple popsicle sticks. And it failed where those beams kind of come together, where the joint is for all those beams where they were glued together. I'm not sure if there's an opportunity to be interactive about this. Can we put out there if anybody has a guess as to what kind of weight that bridge supported?
Yeah, so if you're listening and you'd like to answer that question, just include that in the tweet, I guess, to Ask PIR, and maybe we can hear some feedback from kids on that.
So in the meantime, I'll just show kind of what some of the properties of this bridge. Most of it you can see is made up of multiple popsicle sticks glued together, and that's what gives it its strength, because individually popsicle sticks are very weak, right? And you'll see, some of these, vertical members, that they're too made up of multiple popsicle sticks. You can they've been fitted together to fit in there together. So this actually was an example of an excellent bridge because it was very simple in design, very close to a triangle shape, and it actually supported a huge amount of weight. Do you know if there's been any guesses as to the weight supported?
Oh, let's just see. We've got a few things coming in here. I don't have any guesses yet, but I do have a couple questions that are somewhat related.
Sure.
So, Miss Carruthers' class, she had, there's a question from Grace and Carter. Carter's question is, and you may have just answered that, but just to refresh, what's the strongest design?
Okay. And I actually have some images of that. Typically, a good way to define a strong design for bridges is the ones that can be the longest without any columns in between. And the longest are bridges that use cables. So either suspension bridges or cable-stayed bridges. And let me see if I can bring up images of one or the other. So this here is a cable-stayed bridge. Okay. Is that showing up? So you'll see there are central pillars and then almost ropes coming down, but those are cables coming down from that central pillar to hold up the deck on which you're walking or driving. This is a very strong design. Another one is the suspension bridge. Is that showing up too?
Yeah, we can see that as well.
So this is excellent. So this is actually the world's longest main span. So the span between the two towers is the largest in the world for this type of bridge. It's over 1 kilometer, and it's in Japan. So if the length of the bridge is what we're going to use to measure its strength, these two types of bridges are the strongest one.
So I have an interesting fun fact about popsicle sticks before we go to the next question. So for all of you kids out there, the popsicle was invented by an 11-year-old boy named Frank Epperson. It was purely by accident. He left soda water on the back porch, and because of the cold weather, it stuck to the popsicle stick, and thereby the popsicle was born back in 1905. So for all of you 11-year-old kids out there, stick with it. Stick with it. You never know what's going to happen. And I don't know if Frank would know that 100 years or so later, the popsicle stick and the popsicle itself would be so popular and used, of course, for engineering purposes. So I think that's hilarious.
Yeah.
Anyways. Okay, another question from Grace. What materials would be best to use to build a model of a bridge?
A model of a bridge. Okay. So that's a fantastic question. The answer to that is we can't simply use exactly the same materials for the model of a bridge as for the real bridge, right? It just doesn't work that way for engineering. So what we have to do is use material that's going to mimic. It's going to behave the same way in a smaller size as the big one. So typically we'll use mixtures of some metal, but usually it will be some form of balsa wood, which is basically a lighter version of this kind of wood, and it bends very well. Sometimes we'll use some form of plastic that can be shaped and sized, but usually wood and some little bit of steel in it too is what we use. That's an excellent question. We basically have to be able to pick the right material so we can make sure that the model of the bridge behaves like the real size bridge. Great question.
Here's a comment, not so much a question, but a comment, and I think it's a lovely one, and I'd like to thank Ms. Clark's class for it. Hi, Ms. Clark class. Thank you for this. She would like us to know that the grade 3s are really enjoying the PIR live event today. So I have a feeling that's more directed upon you, Francesco, than to me, but, and that's fantastic. Thank you, class of Ms. Clark. On that note, we've had one last question come in do we have time for one more, do you think?
Absolutely.
Okay, let's do it. So this is from Curtis, and again in Miss Carruthers' class. So Miss Carruthers, you're very popular today. Fantastic. Hi, everybody. I think this is in response to your question regarding the weight. So it looks like they've taken a poll. I'll hold up my phone here so I can read this. Hudson says 62 pounds. Aspen says 47 pounds. Jasmine says 26 pounds. Curtis says 100 pounds.
Are you ready for this? So this bridge actually supported, before it failed, a little over 600 pounds. So that's the beauty of engineering. You're able to use something that is as weak as a popsicle stick. You put it together in a specific pattern. You use science and mathematics to understand that pattern, and you can build something that can hold 2, 3, 4 of me. And that's really amazing, considering this is, as you can see, a relatively small structure, right? So that's the great thing about structural engineering, civil engineering. I mean, you can do amazing things. So 600 pounds, guys. Incredible.
That's incredible. So Curtis, I guess you get the prize. So I'm not sure what Miss Carruthers is going to do for you for winning that. But good job. And before we sign off, and I'm sorry we're going to have to, for the interest of time, let Francesco go pretty soon. But before we do, I just wanted to give you an opportunity, Francesco, to point people towards some more information about you, your students, and projects you've been working on.
Sure. I tend to do a fair bit of work with our upper year students, the ones that are graduating. I allow them to spend a whole year to practice or to learn about something that they're interested in. And I'll be creating a YouTube channel, a YouTube webpage, which I'll pass on to VROC and PIR to share, that actually showcases some of these projects in videos that are 2 minutes or less. You'll get to see some of these people using really knowledge that is simple and common to solve very interesting and complicated projects, like what's going to happen with the soil of a tennis court, or how do you make sure that a house made out of tire will stay up. So hopefully I'll be able to get that out to you guys, and you can all have a look at this. These are really some amazing projects that some of our students are doing, and they can be inspirational. They're really, really cool.
Excellent. So how are we going to share the YouTube channel address? Should we put it? You'll forward it to me, and I'll put it up on our website for people to see, or we'll do a blog post about this. I guess I'll include it in the blog post.
Yeah, that would work too. And I was wondering, would we be able to share it maybe on your Twitter feed?
Absolutely. Yep. By all means. We'll put that up on the PIR hashtag Twitter feed, post show as soon as I get it from Francesco. So that's fantastic.
Yes.
Well, thanks everybody for joining us today. This has been a lot of fun for me. Thank you, Francesco. I'm sure it's been fun for you as well. And
it's been great.
I really appreciate the time to talk with us today. All right, thanks everybody, and we'll see you again next week. I'm sorry I don't know what the show is off the top of my head next week, but check the website. I'm sure it'll all be up there. And thanks again, and have a great week, everybody. Take care now.
Take care. Bye-bye.